All right, we are back. This is Calc 1. I am Mr. Poleggi. We are looking at section 2 of chapter 6, 6.2. Note packet, pages 5 through 8. I'm going to jump to page 5, exponential, growth, and decay. Oh boy. So, yeah, and we're going to do a little more with the separation of variables. And again, we're going to revisit that, but let's look at the first example. So y prime is equal to 5x over y. So first thing we would want to do is we don't want it Newtonian. We want it Leibniz. So dy dx is 5x over y. And now we kind of want all the x's on one thing, all the x junk, and all the y junk. That's not an official math term, but that's kind of what's going on. So we could, oh heck, go way back to algebra and cross multiply. Remember cross multiply? So dy y equals 5x dx. And then what, just rearrange that. So it's y dy equals 5x dx. And now you've got all the y stuff here and all the x stuff there. And now when you do the integration, this is all y. So that's y squared over 2 plus kind of c1 equals 5x squared over 2 plus c2. And then what you're doing with the whole C1 and the C2 thing is it's it doesn't matter. It's a constant. So, you know, if this were 7 and this were 3 and then the overall would be 10, it's all just a constant. And so at the end of the day, I could just say C2 minus C1 is equal to C. And then that's what we're going to put down. And so, hold on a second. I lost, did I lose a 2? No, I didn't lose a 2. So if we multiplied everything by 2 to like kind of solve it for y squared here. First of all, you could leave it as 5 halves and 1 half y. That would be fine. But we could multiply everything by 2. Both sides of the equation. And so now look at what we have. We have y squared plus 2c1 equals 5x squared plus 2c2. But at the end of the day, we could move this over. And we could just say, okay, I have another constant, which is always equal to 2 times C2 minus 2 times C1. This is always true. And then just replace that with C. So we're going to do that little maneuver a lot, where it's just some constant. We kind of did that. I explained that a little bit in chapter 5 with the constant stuff, where we just kind of excluded it from being distributed to because it doesn't matter. So like C1 times 5, I could say that's what C is equal to. And so we just don't do the times 5 thing. So there it is. That is our general solution. Now again, if you would have left it as 1 half y squared equals 5 halves x squared plus c, that's also fine. All right. So let's look at growth and decay. If y is differentiable function of t such that y is greater than 0, y prime is equal to ky. For some constant k, then y is equal to c times e to the kt. Oh, all right. So here, let's identify some stuff for you. For your notes, we're on page 5. We're halfway down. So rate of change of y. And so a lot of people think that was like oh, it was a miscue. It's not. When it says many application problems state that the rate of change of a variable y is proportional to the value of y. That's not a mistake. People are like, oh, wait, that was supposed to be y and t or something. Nope. Nope, nope, nope. That's correct. If y is a function of time, the proportion is written as dy dt is equal to ky, where k represents a constant of proportionality. So we've got the rate of change of y is a, wait. Nope. That's going to be dy dx. Is means equals, remember, is means equals. And then k is constant, and then times y. So that is proportional to y. All right, and so what does that mean? That means when you have this, y equals c e to the kt, or we could call that, you might see it like this in other texts, y equals y naught, like y sub 0. That's y naught. That's usually our initial condition. E kt is a solution to the differential equation y prime equals ky. All right. It will likely make a little more sense as we push through some examples. So here, let's look at the proof. Why does this work? So y is equal to c e to the kt is a solution to y prime equals ky. So let's show that. Let's show this. So let's first rewrite this as dy dt equals ky. All right, so rewrite y prime is the first thing. Now let's make it dy is equal to ky dt. So multiply both sides by dt. And then let's divide. Remember, we want the y separation of variables a little bit here. We want the y's over here. So you got kind of 1 over y dy. We're doing the integration of that. And then here we have the integration of k is a constant, and that's in terms of t. So when we integrate k dt, that's going to just tack a t onto it. So this is what we have. The natural log of y, and I don't need the absolute values for this guy, is equal to kt plus, we'll call it c1, but we're going to do that little trick that I already explained. All right. And officially, yeah, there's like a C1 and a C2. And let's pretend I had another C over there already and I moved it over and that was C1. All right, so now what? Well, I don't want the natural log, so I'll do the little e, apply e. So remember how that works? There's a couple of ways to do this. You could say this is log base e. So some of you old school might have been taught this. I equals kt plus c1. So this is how I usually do it, but I'm gonna do it like this because I know the teacher that teaches Calc 2 does it like this all the time. So I'm going to always demo it like this. But I know if you understand logs are just a fancy way of writing exponents. So this is just the base, ln, log base e. That is e to this power is equal to that, y. And so that's usually, I don't do any of this work, but I'm going to do this work because I know the next teacher that's going to teach it does it like this with e ln y equals e. This is called like applying e. So you still get to the same spot because then this e to the ln y is just y. And then this e to the kt. Now remember, when you're adding exponents, that's the same as multiplying like bases. So I could kind of split this up like so. Okay. And so remember, just do a quick recall here. X squared plus x to the third, or not plus, times. X squared times x to the third was equal to x to the 2 plus 3, which is equal to 5. So if I can go this way, I can go back the other way. I could take something that was added and then split it into two things. And that's what happened right there. So it was being added, and I just split it to the like base things being multiplied. Now, I can just say e to the c1 is just c. It's just some constant. It's just c. And there we are. Our general solution. So we took this and proved this. Okay. Lovely. Let's look at page 6. Page 7 and page 8. Okay. So 6, what are we going to do? So page 6, we're going to find the initial condition. Here, I'll have you write 3 little steps on the tippy top of the page. You can follow our introduction to differential equations. But not really, because like I said, we've been playing with these for a little bit. We just weren't calling them differential equations. All right, so number 1, find u naught, or y naught, using given conditions. Number 2, use y naught and other conditions to find f. And then 3, answer the actual question. Always good to answer the question they ask. Okay. So here, let's read the example. The rate of change of y is proportional to y. Not a typo. That's what it's supposed to say. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? Okay, so this is what we can do. Number 1, when t equals 0, y equals 2, and we're going to find y naught, or y sub 0. Usually the sub 0 is just naught, okay? So let's write down our general form, e to the kx. So this is true. That's the c, e to the kx that we had on the page before. We're just using y naught instead of c. all right, as an initial condition. Physics people always with this initial condition and not, all right? So now we put in our 2 and we put in our 0. And now remember, anything to 0 power is 1. So this is really just 2y0 times 1. So y0 is 2. And when you work in this equation over and over again, and they give you an initial condition, you can just go right to there. You can just jump to right there without all of that. For that one thing. Otherwise, show me the 0. Or you can show me the 0. I wouldn't mind. All right. Always good to put down too much information than not enough. 2, especially in tests. So now we know y0 is 2, and we know t is 2, and y is 4. So now we want to find k. So let's do that. So now we're going to take this, and we're going to say, well, 4 is equal to 2, because we just found that. E to the k, and then when y is 4, x is 2. And so we're going to solve this. So let's say divide by 2. So we have e to the 2k is equal to 2. Okie dokie. So now ln is the way out of this. So if you take the natural log of both sides, again, you could write log base e of 2 is equal to 2k, but that's, again, not usually how Calc 2 teacher teaches it. So she applies the natural log to both sides. And now when you have ln of e to some power, you can just bring that down, and that's just 1. So it's just 2k is equal to ln 2. And then divide by 2. So we got k is equal to 1/2 ln 2. And so now we have k. Now, for these purposes, just because we're just doing this, we can do an approximation. We'll do an approximation of 1/2 ln 2. Click that into your calculator, 0.5 ln 2, and we'll go out 4 decimal places. So k is approximately 0.3466. All right. But if you were on the test and you're not using a calculator, then you would just take this whole thing, 1/2 ln 2, and put it right back into there, you know. All right. Okay. So now what do we have? Well, we have a general form now. We have y is equal to 2, because we found that, e to the 0.3466 t. Okay, so y is equal to 2 e to the 0.344. Oh, yeah. And in the book all the time, they always do 0 point. I'm lazy that way. I'll just do point a lot of the times. So like here, if you want us to go 0 point, it's not a mathematical thing. It's a typeset thing. So the reason books do that all the time is because they're worried if they lead with a decimal that you won't realize the decimal is there. So to kind of scream that there's a decimal there, they put a 0 first, because you never have 0 first. And so that's why they do that. But I often don't do that. All right. So there we are. And now they want us to answer the question. So here's the question. We've got our nice little equation here. And now for 3, it says find y when t is 3. 0.3466 times 3. And then when you do that in your calculator, that'll be approximately 5.657. All right. If you're taking the test and you don't have a calculator, not using a calculator, that's fine. It's just you wouldn't put this answer down, obviously, because you're not going to have that stuff in your brain. What you would have put down would have been y is equal to 2e to the 1/2 ln 2 times 3 power. And then that would be your answer on the test with no calculator. With calculator, you can give me the approximation. I think on the homework, they're going to want the approximation most of the time like that. All right? Lovely, lovely. Okay. Let's look at the second one on page 6. So we're on page 6 of the notes. Suppose that 8 grams of radium. Oh, this is a kind of depressing real life problem. So how long does it take 8 grams of radium to become 1 gram of radium? If it's got a half-life of 1,599 years. So a half-life means if I had 20 grams of radium, to get down to 10 grams of radium, it would take 1,599 years. So suppose that 8 grams of radium is released in a nuclear accident. How long will it take the 8 grams of radium to decay to 1 gram? Radium has a half-life of 1599. Okay, so let's go. Oh, and this one is a test question. There will be one like this on the test. Put a little star on it. Test question. All right, so let's see. T is equal to 0 when y is equal to 8. That's our initial condition. So find y naught. And again, you don't have to, you could just say y naught is equal to 8. You can, if you want to, you can say that y is equal to y naught e to the kt, and then you could say 8 is equal to y naught e to the k times 0, and then you could say 8 is equal to y naught e to the 0, and you could say 8 is equal to y naught times 1, and then you could say 8 is equal to y naught. But honestly, I'm okay with you jumping right here. Initial condition, 8. Got it. All right, so now what do we have for number 2? We have y naught is 8. We know t is 1,599, and we know y is 4. Now, how do we know it's 4? They didn't say 4 grams anywhere, but that's half of 8. So if it's got a half-life of 1,599 years, that means half of it is there in 1,599 years. So that's where the 4 came from. All right, so now find K. So now we're going to go and do the same thing as we did before. Y equals, we got the 8, e to the kt, and now we got the 8. We're going to put in the 1599 equals 8e to the k t. Oh, wait, I put the wrong thing in the wrong spot. Sorry. Y is 4. Y is 4. 1599 is t, time. All right, so now it's always good. It's a half-life, so even without the 8 and the 4, it's going to be always 1/2. If they would have said it was 20 grams, how long to get to 10, that's going to be 1/2. Again, it's a half-life. All right, now we're going to do the natural log, both sides. And then that allows us to basically take the power, the exponent, pull it down. That's 1 times that. So 1599K is ln 1/2, and then divide by 1599. All right. So when you take the natural log of 0.5 and then divide by 1599, you get, I'll put the 0.000433. That is my constant. So now the half-life model looks like this. Y is equal to 8 times e to the negative . Oh, did I leave a negative off of there? 0.000433 t. I think I left a negative off of my answer here. Clear, and then yeah, I left the negative off. Ooh, don't forget that negative. That's important. And then divide by 1599. We'll just confirm the number. You betcha. 4333, 488. Okay, so let's add that negative on there. All right. So now, here we have it. Kind of our general model. And now let's answer number 3. They wanted to know when that's 1, how much time is going to elapse. And so you divide out the 8. And natural log both sides. Pull that down, so negative 0.000433t is equal to the natural log of 1/8, which we divide by negative 0.033. And now, when you divide that, it's a little depressing. It's approximately 4,802.41 years. That's why we are so cautious with radioactive things. All right. So again, if you weren't using a calculator on the test, this one would be a little more complicated than the last one because you got 1 over 1599 ln 1/2. That's what would go there. And then you would take that and solve it out. You know, you'd still solve for t, but it would just be this big clump there with the natural log of 1/8 and all that underneath. All right. Okay. Let's look at page 7. So page 7, the number of bacteria in a culture is increasing. Ooh, this is a good problem. You're going to have to write really small. I really fill up that whole page on that one. So number 7. Page 7, rather. Page 7, example 3. Number of bacteria. So this one's a little tricky because they didn't give us an initial reading on the bacteria. So there's no initial reading. There's no t equals 0. So we're still going to use y equals y naught e to the kt. So the number of bacteria in a culture is increasing according to the law of exponential growth. There are 125 bacteria in the culture after 2 hours, 350 after 4 hours. So we're going to kind of use a system of equations to find the initial condition, to find y naught. So let's take a look. When t is equal to 2, y is equal to 125. So we take this equation, and now we put in 125 equals y naught e to the 2k. And then solve for y naught. So divide e to k, e to 2k. So here we have y naught is equal to 125 e to the negative 2k, right? And when you're dividing by that, you can just move it up and make that negative. So there we have one piece of information. Now let's use t equals 4, y equals 350, y naught is equal to 125 e to the negative 2k. And now let's find k. So we're using kind of a system of equations here in that 350 is equal to 125 e to the negative 2k. And now e to the 4k, because 4 was for the 350. And so all we did was we subbed in this, there, this, still k, and t was 4, and y was 350. All right? So those are like bases. So we can add exponents. So we got 350 equals 125 e to the 2k. Negative 2k plus 4k is positive 2k. Then divide that with the 125 and divide by 25, top and bottom. That'll reduce to 14/5. And then natural log both sides. And so we got 2k is equal to ln 14/5. So divide by 2. So we have k is 1/2 ln 14/5. So now we know what k is. K is equal to approximately 0.5148. Now what we can do is take that and plug in k to find y naught. So sub in k to find our initial condition. So y naught is equal to 125 e to the negative 2 1/2 ln of 14/5. Okay. So that's what it would look like if you didn't have your calculator. Oh no! We did have our calculator, so we kind of figured out what k was. So we didn't need all that stuff. So here, y naught is equal to, or approximately, 44.64. And yeah, microbiologist in a class said that you can't have pieces of a bacteria. So we won't round it to 45. We'll call it 44.64 bacteria. All right, so now we have a particular solution. All right, so what does that look like? Our particular solution. is y is equal to our initial 44.64 e to the 1/2 ln 14/5 t. All right, so now I am using the 1/2 ln 14/5 here instead of 0.5148 because this has round off error in it. And we're talking about bacteria, and they want to know how many are there after many, many hours. All right. Oh, if you're wondering, why did we put in -2 for the time? Because it was 2 hours. We had to put in, we can't put in 0 there. That'll zero everything out. So the first reading we had was 2 hours. And so to get time to 0, we were thinking 2 hours before, since this is what we based all this stuff on. So that's where the -2 came from. Just so you know. If that came, I just looking over the thing and going, I wonder if anybody's going to wonder why that happened. All right, so find y when t is equal to 0. Well, we don't really have to do that. I thought they wanted to know. Oh no, they just want the initial population. Oh well, we had that already. That is the initial population. That's it. So you could put in 0 now into this formula, into our particular solution, but it's just going to be that because it's e to the, that's times 0 now. 14/5, and then that all times 0. So that's e to the 0, which is 1. So at time 0, y is 44.64, which is also known as our initial condition. Why not? Which is what we calculated up there. So that was really not necessary to answer the question. We answered it when we found why not. All right, bacteria. But that was a little tougher because they didn't give us the initial. So we had to first sub those in, solve that out with a variable in it, and then put that into this to find our k constant. And then we left it 1/2 ln 14/5 because we didn't want round off error. If we would have just put in 0.5148, I don't know we would have gotten that back out. All right. So write an exponential growth model for the bacteria population. Let t represent time in hours. Okay, we kind of did this. Here, we'll do it a little piece at a time now. So that was all the work. So y is equal to 44.64 e to the, we'll use the approximation, 8t, where time is in hours. And y is bacteria. Use the model to find it after 8 hours. Oh, okay, so and again, this is going to be an approximation because we're going to 10,000ths place here and only 100ths place there. So all right, and then after how many hours will the bacteria count be 25,000? So now what we're going to do is we're going to take this, say 25,000 is equal to 44.64. e to the 0.5148 t. So we don't know t this time. Divide 44.64. And now again, we've been doing this trick a lot. Give myself a little room. Here, I'll tell you what, I have different colors. I'll use red. Let's do the natural log of both sides. And then that comes down. And we got the natural log of 25,000 divided by 44.64. And then we divide that by 0.5148. And so t is then equal to about 12.29 hours. And we're going to make that squiggly. When you see the squiggly, that means approximately. It's an approximation. All right. Lovely, lovely. Let's look at page 8. 4 months after it stops advertising, a manufacturing company notices that sales have dropped from 100,000 units per month to 80,000 units per month. If sales follow an exponential pattern of decline, what will they be after another 2 months? Oh, declining sales. Using our beautiful math just to make some money. What? Let's see if we can do this. Exponential decay. So, again, there's our general form. So let y equal the units of sales. And t equal time in months. And so we know our initial condition, why not, was 100,000. And then we also know after 2 months, it was down to 80,000, or 4 months. 100 units to 80,000. If sales follow an exponential pattern of decline, what will they be in another 2 months? Yeah, 4 months after. 4 months after. So 4, comma 80,000 is a point. Okay, so let's do that. Let's take t equals 0, y equals 100, y naught equals 100,000, and that determines y naught. Oh, I already did that. Oh my goodness, sorry, my work is all discombobulated here. Here, let me draw a line. Whomp. There we go. So let's start. T equals 0 means y is equal to 100,000, which means that we're going to find y naught, but that is our initial condition. It's 100,000. Again, you could put in the 0, e to the 0, and then that's times 1, and then it's just 100,000, but this is it. Okay. All right. So we got that. Now, let's take that information. So we know y naught is 100,000. And we know when t equals 4, y is equal to 80,000. And let's put all that in and find k. So we're going to take 80,000 is equal to 100,000 e to the 4k. Divide by 100,000. Kill a bunch of zeros, that's 8/10, which is 4/5. And that's e to the 4k. And now let's do the natural log. Both sides, pull 4k down. And that's the natural log of 4/5. And then divide by 4. So 1/4 ln of 4/5 is equal to k. All right. So k here is approximately negative 0.0558. All right. So what does that mean? We have a model. Our model is y equals 100,000 e to the negative 0.0558t. It does make sense that this is negative because it's decay. It's exponential decay, so that moves this down to the bottom. So you're dividing by e to this power, which makes it smaller. So now they want to know after what? 2 months. So 2 months past our 4-month period. What does that make it? 6 months. So when t is 6 months after the initial condition of 100,000, we got y equals 100,000 e to the negative 0.0558 times 6. And then that is going to be approximately 71,554 units. Oh no. It's dropping exponentially. Okie dokie. Oof, that's a really ugly L model. All right. Let's look at the next one. The rate of change of n is proportional to n. When t is equal to 0, n is equal to 250. When t is equal to 1, n is equal to 400. What is the value of n when t equals 4? Okay. All right, so for number 5, when t equals 0, n equals 250. When t equals 1, n equals 400. All right, so that means n naught is 250. All right. So you could say t is equal to 0 and n is equal to 250. Find n naught. But that is our initial condition. It's just going to be 250. All right. So now let's take that and say 400 is equal to 250e to the k times 1. Okay, well, that's easy enough. So divide by 250. So e to the k is equal to, what is that, by 58/5, right? 40 25ths, 8/5. So ln 8/5 is equal to k. Right? We're catching on to that trick, right? All right, so now if I do an approximation, that is 0.470004 is approximately k. And so what does my model look like? Let's set up my model. That is n is equal to 250e to the 0.47000. How many zeros there? 3? 1, 2, 3. Yep, 3 zeros and a 4. K, t, that is k, that's times t. And so there's our model. And again, going back to like the original, this would be dn dt is equal to kn. That is our differential equation right there. And so then n is equal to n kt. So just a quick little translation from the y's. This was normally y and y naught and e to the kt. They just swapped out the y with an n. So it's all the same stuff. Same. Arose by any other name. All right, and then find n when t is 4. So, oh, this will be equal to 250e.47004 times 4. And then when you put that in, that kicks out about 1638.4. I don't think they gave us any what we're working with. You know, they didn't tell units, I guess. You could just say units. All right. Number 6. Oh, what do they say about doubling time and half-life? Are basically, it's the same. It's the same. If you figure out the time it takes to double, and you figure out the time it takes for half of it to disappear, it's the same formula. It's just one of them is going to have a negative power on it, and one of them is going to have a positive power on it. So that's k. That's what the k is. So that's why we could use the same formula. All right, so it says the population of fish grows exponentially. A pond is stocked initially with 500 fish. After 6 months, there will be 1,000 fish in the pond. The owner will allow friends and neighbors to fish. After there are 10,000, how long will they have to wait for there to be at least 10,000 fishies in the pond? All right, well, let's find out. T equal time in months, and then find k, that is doubling time, which is going to be ln 2 over k. So it says 6 months. 6 equals ln 2 over k. So k is equal to, right? We just cross multiply and solve. So 6k equals that. So k is equal to ln 2 divided by 6. All right. So now find why not? Well, they don't really have to find that. They gave it to us. That is 500. I mean, you can just say h equals 0, y equals 500, and then make it 0 out. That's fine. All right. So now let's do our model. So what does our model look like? That is y is equal to 500 e to the 1/6 ln 2 times t. All right. So that's just y equals kt. But we found k based on their little doubling time formula. All right, so we're good. That's the model we're going to use. And now we're going to throw in 10,000. They want 10,000 fishies. And they want to know how much time that's going to take. So first divide out the 500. Get it to E. So that's 20. Right, that's 5 into 100, that's 20. E to the 1/6 ln 2 times t. All right, so now ln both sides, so ln 20. And then ln of that is just going to pull this down. So it's going to be 1/6 ln 2t. So 1/6, that's 1 over 6. Let's cross multiply and solve, or multiply both sides by 6. So that's 6 ln 20 is equal to ln 2 t, and then divide by ln 2. All right. And so that is our time. Now, if you just tell your neighbor that, oh, you can start fishing when 6 ln 20 divided by ln 2 happens, they're probably going to want an approximation in months. So let's go with approximately 25.9 months. 26 months for the fish to be at least 10,000. All right, that was it for 6.2.